Okay, now let's move on to a slightly more complicated example where we have a triangular system. And so in this case, we have three nodes, A, B, and C. Right? We know they are truss elements, so they have a cross-sectional area of A and E for all three bars in the system. Now we have, in this case, A, the node A is fixed to the wall here. And we have point B, or the node B, is not fixed. You can see there's a roller here. So basically, you can roll or displace along these vertical directions. And we have C, which is hanging freely in space. Now, in this case, to keep the whole system balanced, what we do is we apply a force on the node C. Now, to make your life easier, we already decomposed the force on the node C into a horizontal one, which is P1, and a vertical one, which is P2. Right? The complicated part here is we have an element BC that's lying, at 45 degrees to the horizontal axis. Now, to make the life a bit easier, we notice that there is a global coordinate system which is pointing X to the right and Y to the top. Right? So notice that we already know how to solve the stiffness matrix element for a truss element that's lying at the angle to the reference frame. The only thing you need to be careful is that the angle given here is 45 degrees to the minus X direction. It's to this direction. If you go back to the slides, few slides back, when we solve the problem, we actually have the angle that is pointing to the positive X direction. Right? This 5 is pointing to the positive X direction, in which we can solve or substitute the angle value into this big block of matrix. So what we need to use, rather than this angle 45 degrees, we need to use the angle which is this one to the positive X direction. In that case, will be 135 degrees. Now, what we need to solve here is the displacement at C, where the forces are applied, and what are the reaction forces at point A and B. Now, we already know we need to use this equation that is related to force and displacement via the stiffness matrix K. We know that the system has three nodes because it's a triangle. We have 6 unknown variables because each node will have two forces, one going on the X directions and one going at the Y direction. Now we have 6 forces and 6 displacement. Okay, so each node we have force going on X and going on Y. So 2 forces on each node. There are 6 forces, and we have 2 displacements on each node. So 6 displacement. Right. So force is a 6x1 vector, and U is a 6x1 vector as well. That means our K, the stiffness matrix, will be a 6x6 matrix element, 6x6 matrix. So among all those variables, what do we know? We know the forces on C. So be a little bit careful because in this diagram we have A, B, and C, but the order of the nodes go to this circular number. Right? This is how the textbook decided to use. So we have node 1, node 2, and node 3. So on node number 2, the x forces is P1 and the y forces is P2. So F2 is P1, F2y is P2. On node number 3, right, there's no forces along y directions, right? Because it is only the supporting force that are pushed the B to along the x direction, right? And we know that displacement, right, on U1 is not going to move along the x direction. It's not a move along the y direction because A is fixed in position. And the only thing on U3, because the roller can only allow node 3 to roll up and down, so the horizontal displacement on node number 3 will also be 0, but we don't know the displacement on node number 2, so this leaves us with 6 unknown variables: f1x, f1y, f3x, u3y, u2x, and u2y, right? And the stiffness matrix, in this case, what we can do is we work out the stiffness matrix element for each of these 3 bars, and we add them up together, right? For A and B, they are twice simple, right? Because for A, you basically see that A only couple along the x direction, right? There's nothing along the y direction. It's only coupling between 1 and 2. So we have U1x, this diagonal bit, as we said before, is the spring constant. There's nothing on the y direction because the bar is going horizontally. So that gives you 0. And similarly, this U2x and U2x is the value of the spring constant in the diagonal bit, right? And because you have the coupling between U1x and U2x, it's only moving horizontally, remember? So that gives you minus Ka and minus Ka in this off-diagonal matrix element. And everything else is pretty much 0, right? So if you understand how to work out Ka, you will be able to work out similarly what's the matrix for element B, which is this guy here. Now for element C, remember we need to use the stiffness matrix that we established before, which is this guy, but noticing that the angle to the x direction is 135 degrees. So that gave me the cos and sine value of 135 degrees, which plug into the equations we have a few slides back. That gives me the KC matrix, okay? Now we need to bring this thing together. Remember that the whole thing, we have 3 elements and 2 directions, so it should be a 6 by 6 matrix. But for each of these elements, it's only a 4 by 4 matrix. So what do? We need to use the trick of 0 padding that we learned before. So to convert each one of these matrices into a 6 by 6 matrix by filling up the missing element with 0, and then you can add them all up element by element to get a final 6x6 matrix, which is showing in these slides here. It's quite a complicated matrix with lots of irrational number here, because you have an angular element goes in the cos and sines theta factors. And if you write that out, that correlates the forces with the displacement displacement at each node. You will have some equations that look like this. Now, of course, this is a lot more complicated than what we've seen before, and in real applications, this will be solved by computers.